In this session, we're going to talk about radar. But before we talk about radar, we still need to know the power relationship between two antennas. So think about we have a situation like this. We have antenna 1, antenna 2, or antenna A, antenna B. And each of them has the effective area for receiving the signal. And associated with the electromagnetic wave, you have a power density transmitted by this antenna and some power density reaching this antenna. And we want to know how the PT, the transmitting power, is related to the receiver antenna power, PL maximum, based on the match load assumption. Okay, so on this page, we're going to derive this relationship between PT and PL. So let's first look at the effective area definition, which is the match load power to the receiver antenna equal to the effective area of the antenna multiplying with the power density on this antenna. And we also know that the definition of the power gain is given by this expression from section 16.4. And U here is the power per solid angle, and this the PT over 4 pi is the in the denominator. So with these two expressions, you can start to relate this PL maxima to this PT. So if you take a ratio of this PL maxima to this PT, you end up having this expression. And on the right hand side, you have AE2, which is the effective area of the antenna 2. And this GD1 is the directed gain of antenna 1. And you notice that there's a 1 over R squared dependence on in this expression, because imagine that when you transmit some power from antenna 1 to antenna 2, the power density is going to be inversely proportional to the R squared. That is why you have this 1 over R squared dependence in this expression. And then we also have the universal constant given by this expression. This is the directed gain of the antenna 1 divided by the effective area of antenna 1 is equal to 4 pi over lambda squared. So if you put this into this expression, then you will have the expression relating PL maxima to PT. And this expression is going to tell you how the receiver power is related to the transmitting antenna power. So this is going to offer you a way to calculate the power received by one antenna given power from the transmitter antenna. And we call this the Friis transmission formula. And there's an assumption for this formula, which is that we assume that the receiver circuit has a match load so that you get the maximum signal on the antenna load. Now we are in the position to look into this radar. Radar is something that you send an electromagnetic signal into space, and there's an object in space which intercepts some part of the radiation power and rescatter it to another antenna. So in this configuration, you're going to see that this antenna is going to receive less power compared with antenna directly receiving radiation power from a transmitting antenna, because there's a scattering process in this diagram. And so we have to first to see how much power is intercepted by this object. So we define the power intercepted by this object to be equal to the instant power density multiplying with a cross-sectional area. And we call this the cross-sectional area sigma BS to be the radar cross-section or backscatter cross-section. And this amount of power is going to radiate into space and received by this receiving antenna. So approximately this power is going to be radiated as a spherical wave into space. And so we can define scatter power density to be S sub S. And if you multiply the total spherical area 4 pi r square, then this value is going to be approximately equal to the intercepted power by this object. And this is the definition of the radar cross-section or scatter cross-section. And with this expression, we can define the SS, the power density, the power density of the scatter signal over the instant power density to be this expression. Basically, you just move this SI to the right hand side and move this 4 pi r squared to the left hand side. And then you end up having an expression to be sigma BS, which is the radar cross-section, divided by the area of the spherical wave reaching this receiving antenna. So apparently, this is a comparison of the area, and we call this the scattering efficiency. And from this expression, you can also define the power density reaching this receiving antenna to be this expression. With this definition, now we can sort of use this as one example to calculate the cross-section area. In this example, you have a plane wave instant on a small dielectric ball, and this small dielectric ball is very, very small compared with the instant wavelength. So this electric field is going to induce some dipole inside this dielectric ball, and assume that the induced dipole is uniform. And we want to know the cross-sectional area, the radar cross-sectional area of this small dielectric ball. And from the electromagnetic one, you knew that the polarization density vector is given by this expression. And the definition of the polarization density vector is nothing more than the summation of all the dipole inside a volume divided by the small volume. So from this expression, you can calculate the induced dipole moment equal to this. You just multiply this expression with the volume, and then this volume is well defined by this spherical ball with a radius of b. So with this dipole moment given by this expression, you can just extract the formula given in section 16.2 for the Hertzian dipole antenna. Because when this plane wave is instant on this dielectric ball, this dielectric ball just radiates like a Hertzian dipole antenna with a uniform polarization, with a uniform dipole moment given by this expression. So just copy down this formula from section 16.2, and with the substitution of P equal to QdL, and because the current is the time derivative of Q, so you drop down this J omega for the phasor expression. So just put this into this expression and then organize everything. You have this scattered field radiated by this dielectric ball. And you also know that if you have a field from an antenna, then you can calculate the power density given by this expression. So with this calculation, you relate the power density of the scattered radiation to the power density of the instant radiation. And with this, the SS and SI available, then you'll be able to calculate the backscatter cross-section or radar cross-section by taking the ratio of S sub S to SI and multiply this term with 4 pi r squared. In the end, you'll be given by this expression. And again, this V is the volume of this ball, and you can just pick up the formula for the volume of a small ball and put it into this expression. So this example tells you how to calculate the backscatter cross-section of a small dielectric sphere. And the methodology is going to be the same for calculating other object in space instanced by an electromagnetic wave. Now, we want to relate the power of the transmitted antenna to the received power of the receiver antenna. And the formula is going to be called the radar equation. Before I show you all the detailed calculations, you're going to see that previously we have phase transmission formula, which is inversely proportional to the square of the distance. But for this case, you have the electromagnetic radiation go into the space, scattered by this object, reaching this receiving antenna. So this means that you'll be expecting there's a 1/r² dependence between this antenna and this object intercepting the power. And there's another 1/r² dependence between the this target antenna and the receiving antenna. So in the end, you should expect a dependence of the 1/r to the fourth of the power for this radar equation. So let's verify this by doing this calculation. So the derivative gain is given by this formula from section 16.4. So you start to have the transmitted power in this expression. And if we just organize this expression to be the power density of the transmitting antenna, then you're going to have this expression. And also from the definition of the radar cross-section, you can also write down this expression. And you see that there's a ST here, that you have ST here also. So just put this into this expression. You'll be able to arrive at this expression. And you start to see that your transmitter power is on the right-hand side. And then you also start to use the maximum power going into the receiver antenna. So if you just put these two expressions together, then you'll get an expression that relates the power transferred to this receiver antenna in reference to the transmitted power from the transmitting antenna. And also don't forget the universal constant, which is the derivative gain divided by the area, equal to 4 pi over the square of the wavelength. So you continue to put this relationship into this expression to get these results. And so you have a formula now relating the received power in receiving antenna versus the transmitted power in the transmitting antenna. And as expected, if you look at this result, the relationship gives you a 1/r to the fourth of power relationship here. And this expression can also be organized into the phase transmission formula, multiplying with the radar cross-section divided by the spherical area defined by the radiation reaching this receiving antenna. And we call this radar equation. And this is very useful because if you know the transmitted power, then you are ready to calculate the received power on this receiving antenna. And of course, you want to maximize the power received by this antenna, so you can play with the parameters in this expression. 在这个小节里头，我们介绍雷达，但是在开始介绍之前，我们先介绍什么是 phase transmission formula。这个公式呢，告诉你说，在空间里头，如果有2个天线，那这个公式会告诉你怎么去计算这个接收天线的接收到的功率是多少。那但是呢，会给定一个传输天线它的送出的功率是多少。那 再来我们介绍了雷达，雷达这个设备呢是有2个天线，一个呢是送出电磁波讯号的天线，那送出的讯号呢会被空间里头的一个物体拦截，拦截的这个电磁波呢会从这个物体重新的辐射出去，到达这个接收天线。那到底呢有多少的这个功率能够重新辐射到接收天线呢？跟一个radar cross section 的定义有很大的关系。那我们后来又算出一个公式，叫做 radar equation，雷达的这个方程式，告诉我们如何去计算这个接收天线能够接收到的功率是多少。如果说你给定一个这个传输的功率的话，那这是这个小节里头所介绍的一些内容。谢谢。